Overview of OpenMP. OpenMP, or Open Multiprocessing, is a set of compiler directives, related clauses, an application programming interface, and environment variables. It helps in creating applications that run on multiple threads. Using OpenMP, you can define parallel regions of code and create teams of threads to execute them. You can specify how work is shared among threads, declare which data is shared and which is private, and synchronize threads to protect shared data. It also allows you to define sections of code that are executed by a single thread exclusively. Why OpenMP? Simplifies parallel programming. Uses compiler directives instead of manual thread creation and management. Portable shared memory standard. Provides a consistent shared memory parallel model across different platforms. Efficient use of multicore processors. Exploits thread-level parallelism to fully utilize multicore systems. Supports incremental parallelization. Allows gradual parallelization of existing serial programs with minimal changes. Low latency communication. Enables fast data exchange through shared memory without message passing overhead. OpenMP is based on the fork-join model, a parallel execution approach where a program alternates between serial and parallel execution. The program starts with a single master thread in the serial region. When it reaches a parallel region, the master thread forks multiple threads, and all threads execute the same code concurrently. The threads share a common memory space. At the end of the parallel region, the threads join back into a single thread, and execution continues serially. At the top, we have the master thread, which controls the execution of the program. The master thread creates multiple worker threads to perform tasks in parallel. All threads connect to a common shared memory. This shared memory contains shared variables and provides a common address space accessible by all threads. Using shared memory allows threads to communicate and exchange data efficiently. In addition to shared memory, each thread also has its own private variables. These private variables are local to each thread and cannot be directly accessed by other threads. Private memory helps prevent interference between threads during execution. Threads can read and write shared memory, but they must use proper synchronization to avoid conflicts. This model enables efficient parallel execution while maintaining data consistency. OpenMP memory model. The OpenMP memory model defines how multiple threads share and access memory. All threads operate in a shared address space, enabling communication and cooperation. Correct and efficient parallel execution is ensured by controlling data visibility and using synchronization to prevent race conditions. Master thread. This is the master thread. It is the main thread that starts program execution. The master thread initializes variables and controls the overall flow of the program. It also creates parallel regions and spawns worker threads to perform parallel computation. Worker threads. These are worker threads. Worker threads are created when a parallel region begins. Each worker thread executes a different part of the program at the same time. Although they run independently, they cooperate by accessing shared memory. Shared memory. This block represents shared memory. Shared memory is accessible by all threads, including the master thread and worker threads. It stores shared data that allows threads to communicate with each other. Any change made by one thread in shared memory is immediately visible to other threads. Shared variables. Variables stored in shared memory are called shared variables. Multiple threads can read from and write to these variables during parallel execution. To avoid race conditions and ensure correct results, synchronization mechanisms such as critical sections, locks, and barriers are required. Common address space. All threads in OpenMP operate within a common address space. This allows threads to directly access shared data without using message passing. As a result, communication between threads is fast and efficient. Private variables per thread. Each thread also maintains its own private variables. These variables are accessible only to the thread that owns them. Any changes made to private variables by one thread do not affect other threads. Interaction between shared and private memory. Threads use private variables for independent computation. Shared memory is used to exchange data and results between threads. This balance between private and shared memory ensures both high performance and correct execution. OpenMP components. OpenMP programs are built using three main components. These components work together to simplify and control parallel execution in shared memory systems. Compiler directives, pragmas. Compiler directives, also called pragmas, are instructions given to the compiler to specify which parts of the program should run in parallel and how threads are managed. They are written using #pragma-omp. If OpenMP is not enabled, these directives are ignored and the program runs normally. Example: parallel for directive. For example, #pragma-omp parallel for divides loop iterations among multiple threads. Each thread executes a portion of the loop concurrently, improving performance. Runtime library routines. Runtime library routines are predefined OpenMP functions used during program execution. They allow the program to query and control thread behavior, such as the number of threads, thread identifiers, and synchronization. These routines provide dynamic control over parallel execution. Runtime library routine examples. OpenMP provides runtime library routines to manage threads during execution. The function omp_get_thread_number returns the unique ID of the current thread. The function omp_set_number_threads sets the number of threads to be used in a parallel region. Environment variables. Environment variables control OpenMP program behavior externally, without modifying the source code. They are commonly used to tune performance and test different execution configurations. Example: omp_num_threads. For example, the environment variable omp_num_thread specifies how many threads are created during parallel execution. This allows flexible control over parallelism without changing the program. In the center, shared memory is accessed by all threads, so synchronization is essential. On the left, #pragma-omp critical ensures that only one thread at a time enters the critical section, protecting shared memory from race conditions. Below that, #pragma-omp atomic is used for simple operations like x++, allowing safe and efficient updates to shared variables. On the right, #pragma-omp barrier forces all threads to stop and wait until every thread reaches the same point. This ensures that all threads complete a phase before moving forward. At the bottom right, OpenMP locks, such as omp_lock_t, provide explicit control over access to shared data. Together, critical sections, atomic operations, barriers, and locks ensure correct and safe parallel execution in OpenMP. Purpose of OpenMP synchronization. OpenMP synchronization mechanisms are used to ensure correct and consistent access to shared variables when multiple threads execute in parallel. They prevent race conditions by coordinating thread execution and by controlling when and how shared data can be accessed. OpenMP provides several synchronization mechanisms to manage safe access to shared memory during parallel execution. #pragma-omp critical. The critical directive ensures that only one thread at a time executes a specific block of code. It is used when multiple threads need to update shared variables. By enforcing mutual exclusion, it prevents conflicting updates and guarantees correct results. #pragma-omp barrier. The barrier directive synchronizes all threads at a specific point in the program. Each thread waits at the barrier until every other thread reaches the same point. This ensures that all threads complete one phase of execution before continuing. #pragma-omp atomic. The atomic directive ensures that simple operations on shared variables, such as increment or decrement, are performed as a single, indivisible operation. It provides a lightweight and efficient alternative to critical sections for simple updates. Locks, omp_lock_t. Locks provide explicit control over synchronization. A thread must acquire a lock before accessing shared data and release it afterward. Locks are useful in complex synchronization scenarios where finer control is required beyond OpenMP directives. Applications of OpenMP: scientific simulations, weather forecasting, fluid dynamics, astrophysics simulations. Matrix and linear algebra computations, parallel matrix multiplication, solving systems of equations. Image and signal processing, parallel filters, transformations, real-time data processing. Machine learning preprocessing, parallel feature extraction, data normalization. Engineering and numerical analysis, finite element analysis, structural simulations, optimization tasks. Bioinformatics and computational chemistry, sequence alignment, molecular modeling, protein folding.